How much do you really know about the Milky Way? Even if you know your favorite cafes or shortcuts to dodge traffic in your city, chances are you haven't explored every alley or hidden corner. Likewise, the Milky Way, our galactic home, holds many secrets, even for scientists. This awe-inspiring galaxy is filled with celestial phenomena: stars, supernovae, nebulas, energy fields, and elusive dark matter. Let's take a closer look at the incredible mysteries and facts about the Milky Way that may change how you see your place in the cosmos. A sky full of countless stars. Trying to count stars in the night sky is nearly impossible, and astronomers themselves struggle with it. Most stars remain obscured by interstellar dust, and telescopes can only detect the brightest ones. One common estimation method involves observing how stars orbit within the galaxy to estimate its mass. Dividing that mass by the typical mass of a star gives a rough estimate. Using data from the European Space Agency's Gaia mission, around 1 billion stars have been directly mapped, merely 1% of the total. That implies our galaxy may house up to 100 billion stars or more. Imagine if each of those stars hosted just 2 planets. The probability of extraterrestrial life increases dramatically. The galaxy's cosmic isolation. The Milky Way is not tightly packed into a cosmic city, but instead drifts within a vast, relatively empty region of space. The structure of the universe resembles a gigantic web with filaments of galaxies and massive voids. In 2013, researchers Keenan, Barger, and Cowie identified a particularly sparse region, now called the KBC void, which encompasses the Milky Way, the Local Group, and much of the Laniakea supercluster. We truly live in a lonely pocket of the cosmos. A glimpse of the beast within. At the heart of our galaxy lies a monstrous black hole, Sagittarius A star, with a mass equivalent to 4 million suns. Its existence was inferred from the orbits of nearby stars, but now we have an actual image, thanks to a collaborative effort using radio telescopes. This supermassive black hole joins an elite group, part of the estimated 100 billion such objects in the universe. Out of 40 quintillion black holes, only a fraction are supermassive, making Sagittarius A extraordinarily rare. Stars from distant galaxies. Like cameo appearances in films, stars from other galaxies sometimes wander into the Milky Way. Researchers hunting for hypervelocity stars, those ejected at extreme speeds from galactic centers, found some racing toward, not away from, our galaxy. These stars may have originated in the Large Magellanic Cloud, a satellite galaxy orbiting the Milky Way. This discovery hints at ongoing galactic interactions and migrations. Our galaxy's unstable companions. Centuries ago, explorers like Ferdinand Magellan documented strange glowing patches in the southern hemisphere's sky, what we now know as the Magellanic Clouds. These are dwarf galaxies still orbiting the Milky Way. However, many of these smaller galaxies don't last long. The Milky Way often absorbs them. In fact, millions of stars following similar needle-shaped orbits suggest that one such galaxy, nicknamed the Gaia Sausage, was consumed by ours. A greasy galactic mystery. Between the stars lies more than just empty space. It's filled with greasy molecules called aliphatic carbon compounds, formed in aging stars and dispersed throughout the galaxy. Recent research suggests there may be far more carbon in the Milky Way than previously believed, potentially 5 times as much. Since carbon is essential for life, this abundance could support the idea that life might exist elsewhere in the galaxy. A collision is inevitable. In about 4 billion years, the Milky Way will collide with its neighbor, the Andromeda Galaxy. The two are closing in at approximately 400,000 kilometers per hour. Previous models predicted Andromeda would dominate the aftermath, but newer data suggests both galaxies have similar mass, around 800 billion times that of the Sun. Whether the Milky Way will survive the collision remains uncertain. Bubbles nobody noticed. Imagine discovering a hidden object in your own living room that had always been there. In 2010, scientists made a similar discovery. Enormous gamma-ray emitting structures called Fermi bubbles, rising 25,000 light-years above and below the Milky Way. These bubbles likely resulted from a massive energy event millions of years ago, perhaps our central black hole devouring a massive gas cloud and ejecting the remains in a fiery blast. The galaxy's mysterious mass. The true mass of the Milky Way remains elusive, with estimates ranging from 700 billion to 2 trillion solar masses. The problem lies in dark matter. It makes up about 85% of the galaxy's mass, but it doesn't interact with light. Astronomers try to measure its effects indirectly by observing how our galaxy influences nearby dwarf galaxies. Recent calculations using this method estimate the Milky Way's mass at around 960 billion solar masses. Strange signals from the stars. Over the last decade, scientists have detected fast radio bursts, FRBs, mysterious, fleeting emissions from deep space. Initially, only a few dozen had been documented, but recent observations have doubled that number. In 2020, 6 unique signals were traced to the center of our own galaxy. They didn't match any known radio emission patterns and were tracked to a source called ASCAP J 173608.2. To better investigate these and similar phenomena, the SKA, Square Kilometer Array, radio telescope is under construction. Once operational, it will produce detailed sky maps daily and might finally solve the puzzle of these baffling signals.
Since ancient times, people have looked up at the stars and wondered, are we alone in the universe? Today, modern science finally has the tools to approach this question seriously. With the advent of powerful telescopes and interplanetary missions, we have begun a systematic search for life, not only intelligent life, but any form of biological activity beyond Earth. Currently, research is focused on 2 main directions: ocean worlds within the solar system and exoplanets orbiting other stars. Despite their differences, these 2 classes of objects share a key feature: the potential presence of liquid water, a fundamental prerequisite for life as we know it. Liquid water is a unique substance with exceptional physical and chemical properties, high heat capacity, the ability to dissolve organic compounds, and participation in biochemical reactions. All known forms of life on Earth depend on it. For this reason, The presence or potential presence of liquid water serves as the main indicator of habitability. Within the solar system, this includes planets and moons with subsurface oceans. Beyond it, the focus is on exoplanets located in the so-called habitable zone. Europa, Jupiter's icy moon with a subsurface ocean. Europa remains one of the primary targets of astrobiological missions. Studies have shown that beneath its 10 to 30 kilometre thick ice shell lies a salty liquid ocean. This has been confirmed by magnetic field data, ice shell dynamics, and observations of potential geysers. In 2024, NASA successfully launched the Europa Clipper mission, which will conduct dozens of flybys in the 2030s to study the surface, magnetic field, and plume composition. The mission is expected to refine estimates of ice thickness, ocean depth, and whether the ocean is in contact with the rocky mantle, a key factor for the presence of chemical energy. Enceladus, Saturn's active and mysterious moon. Enceladus is one of the most intriguing moons. The Cassini spacecraft, which ended its mission in 2017, discovered active geysers ejecting water containing salts, molecular hydrogen, and organics. This suggests hydrothermal activity on the ocean floor beneath the icy crust. Such conditions resemble Earth's deep-sea hydrothermal vents, where life thrives without sunlight. The presence of molecular hydrogen, possibly produced by reactions between water and rock, points to potential energy sources for microbial life. Ganymede and Callisto. Ganymede, the largest moon in the solar system, also harbours a subsurface ocean. Its intrinsic magnetic field makes it unique among moons. The JUICE mission, Jupiter Icy Moons Explorer, launched by ESA in 2023, is en route to the Jovian system to study Ganymede and other moons in the 2030s. Callisto, though less geologically active, is of interest as a cold ocean world, where water may have remained stable for billions of years. This raises the possibility of long-lived, stable biospheres distinct from those on Earth. Titan, a unique laboratory of hydrocarbon chemistry. Titan stands out with its dense atmosphere and liquid methane lakes. Although water is frozen on the surface, a subsurface water ocean may lie beneath. Titan is also of interest due to the active organic chemistry occurring in its atmosphere, potentially analogous to prebiotic Earth. The Dragonfly mission, scheduled for launch in 2028, will deliver a rotorcraft lander capable of exploring various sites and analysing complex organic molecules on Titan's surface. Terrestrial analogues and lessons from astrobiology. Studying extremophilic organisms on Earth is a crucial component of astrobiological research. Life has been discovered in environments once considered uninhabitable. Boiling springs, salt mines, permafrost, under Antarctic ice, and in deep-sea hydrothermal vents. Some of these organisms survive entirely without sunlight, relying on chemical energy instead. These examples suggest that microbial life could exist in the subsurface oceans of moons like Europa and Enceladus. Proxima b, the closest exoplanet in the habitable zone. Proxima b was discovered in 2016 using the HARPS spectrometer. It orbits Proxima Centauri, the closest star to us, just 4.2 light-years from Earth. The planet has a mass approximately 1.3 times that of Earth, and an orbital period of 11.2 days. Despite its proximity to its star, Proxima b lies within the habitable zone due to Proxima Centauri's low luminosity. If the planet possesses a dense atmosphere, surface temperatures could be sufficient to support liquid water. Proxima b is likely tidally locked, meaning one side permanently faces the star while the other remains in darkness. However, a dense atmosphere could redistribute heat, creating stable conditions in the terminator zone, the twilight region between day and night. The main threat to habitability is stellar flares. Proxima Centauri is an active red dwarf that emits intense ultraviolet and X-ray radiation. This could strip away the planet's atmosphere and render it inhospitable. Nevertheless, some models suggest that a strong magnetic field and atmospheric regeneration processes could offer protection. Methods of exoplanet and atmosphere detection. Several techniques are used to detect exoplanets, including the radial velocity method, used to discover Proxima b, the transit method, used by the Kepler telescope, direct imaging, rare but rapidly advancing gravitational microlensing. For assessing habitability, spectroscopic analysis of exoplanetary atmospheres is crucial. This includes the search for biosignatures such as oxygen, ozone, and methane, as well as their relative concentrations. Oceanic exoplanets, a new class of worlds. In addition to rocky planets, there are hypothetical water worlds, exoplanets entirely covered by global oceans. These oceans could be hundreds of kilometers deep, with a high-pressure ice layer at the bottom. In such environments, sunlight may penetrate only the upper layers, but underwater chemical processes could still occur. Some models suggest that these worlds could be habitable even without atmospheres, provided they have internal heat sources. New telescopes and breakthroughs in observations. The James Webb Space Telescope, successfully deployed into orbit in 2022, has already conducted spectroscopic observations of several exoplanets. Although Proxima b remains beyond its current capabilities, JWST has refined the understanding of gas giants' atmospheric compositions and demonstrated sensitivity to water vapor and CO2. Future telescopes. In the 2030s, next-generation telescopes are planned for launch, including LUVOIR, HABEX, as well as ground-based giants like ELT, TMT, and GMT. These instruments will be capable of studying the atmospheres of Earth-like exoplanets, including potential biosignatures. Some missions envision the use of coronagraphs and starshades to block stellar light and obtain direct images of planets. Future missions in the Solar System. Europa Clipper, NASA, launched 2024. Study of Europa. JUICE, ESA, launched 2023. Exploration of Ganymede, Callisto, and Europa. Dragonfly, NASA, launch planned for 2028. Autonomous rotorcraft lander on Titan. Enceladus Orbilander, proposed mission to analyze geyser plumes from orbit followed by a landing. Technologies of the future, cryobots and drilling probes. One of the main engineering challenges remains delivering probes to subsurface oceans. Work is underway on so-called cryobots, autonomous drilling devices capable of penetrating tens of kilometers of ice to deploy underwater probes. This will require nuclear power sources, autonomous navigation, pressure resistance, and complete sterility to prevent contamination of extraterrestrial biospheres. The discovery of life, even microbial, beyond Earth would constitute a scientific revolution. It would prove that life is not unique and can develop under a variety of conditions. Questions such as who are we, where do we come from, and are we alone, would gain a new dimension. Even if life is not found, the very pursuit helps us deepen our understanding of life's nature, its limits, and the diversity of conditions under which it can exist. Modern astronomy stands on the threshold of one of the most significant discoveries, detecting life beyond Earth. Ocean worlds of the solar system offer access to potential biospheres within reach. Exoplanets such as Proxima b expand the search to the nearest stars. Advances in observational technologies, robotic missions, and climate modeling of other worlds are gradually bringing us closer to solving one of humanity's greatest mysteries.
Beyond our planet, at a distance of billions of kilometers, lie unexplored realms. Space is the greatest mystery humanity has ever tried to solve. And among its enigmas, black holes hold a special place. Absorbing light, time, and space, they cannot be seen directly, but their influence is felt everywhere. What are black holes, Why do they frighten and captivate scientists and poets alike? And most importantly, could they one day consume everything we know, the entire universe? Our film is a journey to the frontiers of modern science. We will peer into the heart of a black hole, listen to astrophysicists' insights, embark on a mental voyage across the universe, and try to understand, do we have a chance to escape the fate dictated by these cosmic monsters? In the beginning, there was a super-dense incandescent cloud of matter. It exploded in the Big Bang, giving birth to space and time. Billions of years later, the first stars, galaxies, and then black holes began to form in the universe. When a massive star exhausts its fuel, it can no longer support its own weight. Gravity takes over, the core collapses, the outer layers disperse, and what's left compresses into a point of infinite density, a singularity. This is how a black hole is born. A black hole is not just a bottomless pit. It's a laboratory for testing the limits of our knowledge about the nature of space, time, and matter. Everything that falls in disappears from our universe, or perhaps continues to exist, but in another form. But can these giants grow endlessly? Can they devour not only nearby stars, but entire galaxies? And if so, where is the limit? We will explore what we currently know about black holes and try to answer the main question: can their power plunge the universe into darkness? Gravitational monsters. That's how black holes are often described. But today, they're no longer just a hypothesis, but observable objects. We see stars orbiting what seems to be an invisible center. We detect gravitational waves, the ripples in space-time caused by the merging of black holes, first observed in 2015 by LIGO. With the most powerful telescopes, including the Event Horizon Telescope, humanity has seen the shadow of a black hole, the silhouette of the event horizon around the supermassive black hole in the galaxy M87. It was a landmark confirmation of Einstein's general theory of relativity under extreme conditions.
The event horizon is a boundary beyond which nothing, not even light, can escape. Everything that crosses it becomes part of the black hole. We don't know what happens next. Perhaps it's a gateway to another universe?
There are different types of black holes. Stellar mass black holes form from collapsing stars and usually weigh between 5 and 50 times the mass of our sun. Supermassive black holes, found in the centers of galaxies, can have masses equivalent to billions of suns. In between, we have intermediate mass black holes, rare and still under investigation. Black holes grow by absorbing matter from their surroundings, forming an accretion disk that emits intense X-rays as particles spiral inward. These emissions are a primary method by which we detect black holes indirectly. Another method of detection is gravitational lensing. When the black hole's immense gravity bends light from background objects, creating arcs and rings of distorted images. This confirms their mass and gravitational influence. Even black holes are not eternal. According to Stephen Hawking, they slowly evaporate by emitting what we now call Hawking radiation. This quantum mechanical process implies that black holes lose mass over astronomical timescales, eventually vanishing completely. At the centers of galaxies lie supermassive black holes, such as Sagittarius A star in the Milky Way. Their origin is still debated. Some theories suggest direct collapse from massive primordial gas clouds, while others argue for a slow growth from smaller black holes via accretion and mergers over billions of years. What if such giants keep growing? Could they consume their entire galaxy? Currently, feedback mechanisms, such as energy outflows from active galactic nuclei, appear to regulate growth. But if those mechanisms fail, the balance could tip. Beyond their mass and invisibility, black holes vary in complexity and behavior. Most real black holes are not perfectly static, but rotate. These are called Kerr black holes, named after Roy Kerr, who first solved Einstein's equations for a rotating black hole in 1963. Kerr black holes drag space-time around with them, an effect known as frame dragging. This rotation can lead to the formation of a region outside the event horizon called the ergosphere. In this zone, particles and even light are compelled to move in the direction of the rotation. Some energy can theoretically be extracted from this region, known as the Penrose process. Many supermassive black holes are also classified as active, especially those powering quasars. Quasars are extremely bright galactic nuclei, visible from billions of light years away, where matter falling into a supermassive black hole emits vast amounts of energy. These objects helped astronomers discover black holes long before direct imaging was possible. Another mysterious concept in theoretical physics is the naked singularity, a hypothetical point of infinite density not hidden by an event horizon. If such objects exist, they could violate the cosmic censorship conjecture and expose the raw core of gravitational physics to observation. So far, no such singularities have been found.
If naked singularities exist, they could offer unprecedented access to quantum gravity, perhaps the key to unifying general relativity in quantum mechanics.
This growing knowledge continually reshapes our understanding of the universe. Black holes are no longer just the end of stars. They might be central to galaxy formation, cosmology, and the ultimate fate of space-time itself. Let's consider hypothetical scenarios for the distant future of the universe in which black holes could determine the ultimate fate of everything we know. Could black holes consume the entire universe? Imagine billions of years from now. Stars are dying out. Matter becomes sparse. The universe turns cold and empty. In this darkness, black holes remain, the remnants of former energy and light.
There's a theory of the heat death of the universe. Everything slowly approaches thermodynamic equilibrium. Only black holes will be left. They too will slowly evaporate, and nothing will remain.
The Big Freeze, heat death, the most widely accepted scenario. As the universe continues expanding, galaxies drift apart, stars burn out, and entropy increases. Eventually, only cold remnants like white dwarfs, neutron stars, and black holes remain. Over trillions of years, even black holes evaporate via Hawking radiation. The Big Crunch. If the density of the universe is high enough, gravity might reverse the expansion. Galaxies collapse back together, stars ignite again, and black holes merge. Ultimately, everything might contract into a final singularity, mirroring the conditions of the Big Bang. The Big Rip. If dark energy continues accelerating the expansion of the universe at an increasing rate, it could eventually overcome all other forces. First galaxies, then stars, planets, and even atoms would be torn apart. Black holes would evaporate or be stretched into nothingness. Each scenario depends on the exact properties of dark energy, the total mass energy content of the universe, and the nature of gravity at cosmological scales. But what if the end is not truly an end? Some physicists propose cyclical cosmology, where the universe undergoes infinite cycles of expansion and contraction, a cosmic heartbeat. Others suggest a multiverse, where black holes might spawn new universes with different physical constants, as in the cosmological natural selection theory.
Some quantum gravity models propose that a singularity inside a black hole could bounce and generate a new Big Bang. In that case, black holes may not end everything. They may begin something else entirely.
Could our universe have been born from such a process? These ideas, though speculative, reveal how black holes are no longer just cosmic vacuum cleaners. They might be fundamental to the life cycle of the cosmos itself. From the dawn of time, humans have looked up at the sky. In those stars, we saw gods, myths, and dreams. Today, we see galaxies, supernovae, and black holes. And yet, the questions remain the same. Where did we come from? Where are we going? Is there an ultimate end to all things? Confronting the vastness of the cosmos and the idea of a finite universe evokes awe, but also existential fear. It challenges our place and purpose. But this awareness is what makes us extraordinary. We are made of the same elements forged in stars, and we have the capacity to understand the laws that govern them. Black holes, entropy, cosmic expansion, all are part of a grand narrative, one that we, as sentient beings, are uniquely able to explore. It's not just about survival, it's about meaning. Our desire to understand, to ask questions, to peer into the void is perhaps the greatest expression of what it means to be human. The universe may not care about us, but we care about it. We observe, we study, we wonder. And in doing so, we give the cosmos a voice.
2.5 million years ago, at the heart of Andromeda, a massive star reaches the end of its life cycle. A supernova explosion hurls trillions of tons of scorching plasma into space, obliterating nearby planets and satellites. A powerful electromagnetic pulse races outward, destined to reach Earth millions of years later. 1885, Earth. Astronomers around the world observe an unusually bright flare in the Andromeda constellation. For a brief moment, its light outshines the nearest stars. This supernova, named S Andromedae, remains a mystery to scientists for years. Just 6 months later, it fades and disappears from the night sky. It's important to note that at the time, astronomy lacked the means to measure cosmic distances. Andromeda, object M31, was thought to be just a nebula at the edge of the Milky Way. Only in the 1920s, thanks to Edwin Hubble's observations, did it become clear that Andromeda is a separate galaxy, comparable to our own. Today we know that Andromeda is a spiral galaxy containing about 1 trillion stars. Its diameter exceeds 150,000 light-years, and its mass is estimated between 800 billion and 1.5 trillion solar masses. With an abundance of red dwarfs and relatively little dark matter, it closely resembles the Milky Way. At Andromeda's core lies a brilliant nucleus packed with millions of stars. Their density is so great that their light blends into a single dazzling glow. For decades, the remnants of S Andromedae were undetectable, but in 1988, scientists discovered a nebula which, through spectral analysis, was confirmed as the remnant of that very supernova. A double nucleus, a puzzle for scientists. Andromeda is unique for its double nucleus. The larger, brighter part is a star cluster about 7 light-years across, slightly offset from the center. The smaller, dimmer core likely conceals a supermassive black hole with 50 million times the Sun's mass. Scientists still debate whether this structure is the result of a galactic merger or simply an optical effect caused by a dust lane. Unusual stellar systems. Near the core lies a unique object, a binary system with a neutron star and a red giant. Almost invisible in optical telescopes, it becomes the galaxy's brightest point in X-rays. The neutron star spins every 3 seconds, and the two objects orbit each other every 4 hours. Evidence suggests the neutron star is gradually pulling material from its companion, eventually forming a bright ring-like nebula. Structure and spiral arms. In the central bulge, about 12,000 light-years across, roughly 30% of Andromeda's mass is concentrated. The galaxy also features a bar structure about 17,000 light-years long, which is almost invisible from Earth. From the ends of the bar emerge 2 giant spiral arms, between which stretch dark gaps as wide as 13,000 light-years. The arms hold about 56% of the galaxy's mass and serve as nurseries for new stars. Young stars and giants. Among them is Andromedae, a massive blue giant with a mass of up to 120 suns. Its surface temperature is around 20,000 K, and its luminosity is 500,000 to 700,000 times greater than that of the Sun. The star is highly unstable, periodically unleashing plasma outbursts that amplify its brightness manyfold. In about 1 million years, it is expected to explode as a supernova, leaving behind a black hole. Galactic formation history. The oldest stars, 11 to 13 billion years old, are concentrated in the core, while the disk and spiral arms host younger stars, around 3 to 4 billion years old. Some regions are still stellar nurseries. Andromeda also helps define the hypothetical galactic habitable zone. The center is too radiation intense, the periphery lacks heavy elements, and the intermediate zone offers the most promising conditions. Potential exoplanets. The red giant Mega ML7 drew particular attention after 1999, when gravitational microlensing observations revealed potential deviations in its trajectory, possible evidence of a massive companion. If confirmed, the hypothetical exoplanet Mega ML7b, about 6.3 times Jupiter's mass, would be the first exoplanet ever discovered beyond the Milky Way. Clusters and past collisions. Andromeda hosts around 460 globular clusters and 10,000 open clusters. One standout is NGC 206, a massive star association weighing about 200,000 solar masses. It formed after 2 gas and dust nebulae merged. Many clusters are remnants of ancient cosmic collisions. A notable example is M32, once a larger galaxy. It collided with Andromeda 800 million years ago, losing much of its mass and leaving behind a compact object with a supermassive black hole. The galactic future. Andromeda has about 30 known satellite galaxies. It belongs to the local group, along with the Milky Way and the Triangulum Galaxy. Gravitational forces are pulling Andromeda toward us at 300 kilometers per second. In a few billion years, the two galaxies will merge, forming a giant elliptical galaxy. By then, the Sun will be nearing the end of its life, and what will become of humanity remains an open question. Will we populate distant worlds, or will we vanish without a trace?
What makes a black hole's heart beat? Deep in the cosmos, roughly 28,000 light-years from our planet, something extraordinary is pulsing with an almost biological rhythm. IGR J17091-3624, dubbed the heartbeat black hole, has been sending dramatic, rhythmic pulses of light across the universe, and now it's forcing scientists to question everything they thought they knew about these cosmic giants. Picture this cosmic scene, a massive black hole locked in an eternal dance with a companion star, steadily siphoning matter like a celestial vampire. As the stolen stellar material spirals into the black hole's accretion disk, it forms a swirling maelstrom of superheated plasma that glows with intense X-ray radiation. This feeding frenzy creates the characteristic heartbeat, those rhythmic brightness fluctuations that gave this black hole its nickname. But here's where the story takes an unexpected turn. NASA's Imaging X-ray Polarimetry Explorer, IXPE, recently turned its sophisticated instruments toward this pulsing giant, measuring something called X-ray polarization, essentially tracking the direction and alignment of the black hole's high-energy emissions. What did they find? The results were startling. IXPE recorded a polarization degree of 9.1%, a measurement significantly higher than any theoretical model had predicted. Why does this matter? Think of polarization as a cosmic fingerprint that reveals the hidden architecture around black holes. High polarization typically indicates we're viewing the corona, the superheated region around the black hole, almost edge-on, where matter flows in highly ordered patterns. But here's the puzzle: other observations of IGR J17091-3624 don't support this edge-on perspective at all. Two theories, one cosmic conundrum. Faced with this contradiction, astronomers have proposed two intriguing explanations, each challenging fundamental assumptions about black hole behavior. The wind theory: could powerful winds be launching from the accretion disk itself? These cosmic gales might scatter X-rays in ways that create higher polarization without requiring an edge-on view. It's like trying to understand a hurricane by studying how it bends light. The winds themselves become part of the optical story. The relativistic corona theory: perhaps the corona isn't stationary but racing outward at extraordinary speeds, approaching the speed of light. At such velocities, Einstein's relativistic effects could dramatically amplify the polarization we observe, creating readings that seem impossible under normal circumstances. Computer simulations of both scenarios successfully reproduce IXPE's puzzling measurements, but each model forces scientists to reconsider long-held beliefs about how matter behaves in these extreme environments. What's really at stake? Why should we care about winds around a distant black hole? According to Maxim Parrar, co-author of the study from AIM University, these winds represent one of the most critical missing pieces to understand the growth of all types of black holes. They are not just astronomical curiosities, they're fundamental to understanding how black holes grow, evolve, and shape the galaxies around them. The beat goes on. As IXPE continues its observations and other telescopes join the investigation, astronomers expect even more surprising polarization measurements. Each pulse from this cosmic heart brings us closer to understanding not just one peculiar black hole, but the fundamental physics governing some of the universe's most extreme environments. The heartbeat black hole reminds us that the cosmos still holds secrets capable of overturning our most confident theories. In the rhythmic pulse of IGR J17091, we hear an invitation to keep questioning, keep observing, and keep marveling at the universe's capacity to surprise us. What will the next heartbeat reveal?
Imagine looking up at the night sky and realizing that everything you can see, every twinkling star, every glowing nebula, every distant galaxy represents less than 5% of what's actually out there. What fills the remaining 95% of our universe? This is the story of one of science's greatest puzzles, dark matter. The mystery began in the 1970s when astronomer Vera Rubin made a startling discovery. She was studying how fast stars orbit around the centers of galaxies, expecting to find that stars farther from the center would move more slowly, just like planets in our solar system. Instead, she found something impossible. What did Rubin's observations reveal about our understanding of gravity? Stars at the edges of galaxies were spinning far too fast. According to everything we knew about gravity and physics, these speedy stellar rebels should have been flung out into space long ago. Yet there they were, somehow held in their orbital dance. The only explanation? There had to be something else out there, something invisible providing the extra gravitational pull needed to keep those stars in line. Scientists call this mysterious substance dark matter, though it's neither dark nor necessarily what we typically think of as matter. It's more like a cosmic ghost, present everywhere, influencing everything, yet completely invisible to our eyes and instruments. Current estimates suggest dark matter comprises roughly 27% of everything that exists. Combined with dark energy, another cosmic enigma, these invisible components make up 95% of reality. We, along with every star, planet, and galaxy we can observe, are essentially cosmic minorities, representing just a tiny fraction of what's really out there. But how do you study something you can't see? Astronomers have become cosmic detectives, looking for dark matter's fingerprints throughout the universe. What evidence convinced scientists that invisible matter really exists? The proof comes in three compelling forms. First, there's the galactic spinning problem Rubin discovered. Across thousands of galaxies, the same pattern emerges, stars moving too fast for visible matter alone to explain their behavior. Second, dark matter acts as a cosmic magnifying glass through gravitational lensing. Massive concentrations of dark matter bend and distort light from distant galaxies, creating spectacular cosmic funhouse mirror effects that reveal dark matter's hidden presence. Third, when scientists run computer simulations of how the universe evolved from the Big Bang to today, the models only match what we actually observe when dark matter is included in the calculations. Without it, galaxies simply wouldn't have formed the way they did. Why hasn't anyone captured dark matter in a laboratory yet? The answer lies in dark matter's antisocial nature. Unlike ordinary matter, it doesn't interact with electromagnetic radiation, it doesn't absorb light, reflect it, or emit it. Dark matter particles seem to slip through regular matter like ghosts walking through walls. This ghostly quality makes detection extraordinarily challenging. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to catch the rare moment when a dark matter particle might bump into an ordinary atom. So far, these cosmic fishing expeditions haven't landed the big catch. Other researchers are taking different approaches. Some smash particles together in enormous accelerators, hoping to create dark matter in the lab. Others scan the skies looking for the telltale signs of dark matter particles annihilating each other in space. Could life as we know it exist without dark matter? This question gets to the heart of why solving the dark matter mystery matters so much. Dark matter appears to be the universe's scaffolding, the invisible framework upon which everything else is built. Without dark matter's gravitational influence, the early universe might never have developed the clumps and structures that eventually became galaxies. No galaxies would mean no stars, no planets, and ultimately, no us. Dark matter isn't just a curiosity, it's the foundation that makes our existence possible. The search for dark matter represents more than just solving a cosmic puzzle. Finding and understanding dark matter could revolutionize our grasp of physics, potentially revealing new particles, new forces, or even new dimensions of reality.